Hello everyone, it is a pleasure to welcome you all once again to MSP lecture series on transfer chemistry. Since my last lecture, that is in my 45th lecture, I started the topic inorganic reaction mechanisms. With brief introduction, I also initiated discussion on substitution reactions in square planar complexes. So, let me continue from where I had stopped. So, transmetal complexes having D8 electronic configuration, and we can consider rhodium, iridium, palladium and platinum in +2 state, rhodium and iridium in +1 state, and also gold in +3 state. So, they all prefer square planar geometry with an exception of nickel 2 complexes. They have a tendency to adopt both tetrahedral and square planar geometries even with sometimes strong field ligands. However, majority of kinetic work on square planar systems has been carried out on platinum 2 complexes because the rate of ligand substitution is conveniently slow, so that the mechanism can be established with much easy without going to very fancy fast reaction rates systems and other things. Although substitution reaction data is available for palladium 2 as well as gold 3 complexes, which also show similarities, they are not always follow the same mechanism that is followed by these metals such as rhodium, iridium or platinum. So, let us look into those differences as we progress with this topic. The extensive mechanistic studies on platinum 2 complexes and observed negative values of delta S and delta V suggest that the nucleophilic substitution reactions in square planar complexes proceed by associative mechanisms. Once again I tell you, the extensive data we have on mechanistic studies on substitution reactions in platinum 2 complexes and also observed negative values of delta S and delta V suggest that most of the nucleophilic substitution reactions that we perform on square planar complexes proceed by associative mechanism. For example, if you look into the rate constant for the displacement of chloride ligand by water in tetrachloroplatinate, or you can consider here Cl3 and NH3 having anionic ligand, or you have diamino dichloro or having something like this. If you consider any of these 4 complexes, okay, for substitution of chloride by water, they suggest associative mechanism. The dissociative pathway is expected to show a significant dependence on the charge on the complex. Nevertheless, there are ways to explain substitution reaction in case of platinum complexes or D8 system or square planar complexes using dissociative pathway by looking into some donor solvent interaction which make weak interactions on the axial position to have a tetragonal geometry. So, let us look into those things later. Now, let us consider a typical reaction here, square planar complex of platinum 2 that undergoes substitution. Here again X is the leaving group and Y is the entering group, and we have this one and it is forming here. So, the rate law can be written this one in this format where we are considering 2 terms here, K1 and K2. So, the typical reactions of this type are studied under pseudo first order conditions in the presence of an excess of Y and also solvent S. The 2 terms are there, you should recall. So, the reason is the solvent interference in the substitution reactions. For example, if Y is in large excess, of course solvent is always in large excess, the change of concentration of Y with the time is almost 0. So, that means after a certain time the Y concentration does not change. Similarly, solvent concentration also does not change with time because the minimum change in the solvent can be ignored. So, it more or less remains same. So, that means with respect to time the change observed is 0, and then what happens, the observed rate constant can be simply written as in this format, and that means otherwise K observed equals K1 plus K2 into the concentration of Y. So, K1 and K2 can be evaluated by carrying out a series of reactions with various concentrations of Y. I showed you 2 terms K1 and K2, they can be evaluated by carrying out a series of reactions with various concentrations of Y. For example, let us look into these plots here. The experiments shows that the term K1 becomes dominant if the reaction is carried out in polar solvents, okay, and its contribution diminishes in apolar solvents. So, this indicates solvent participation can be represented by, okay, modifying the equation in this form. You can see here in this one. So, you can see the experiments shows that the term K1 becomes dominant if the reaction is carried out in polar solvents and its contribution diminishes in apolar solvents. You should remember that this indicates solvent participation can be represented by modifying the equation E1 as E2 can see here. So, for example, here we are taking K1 into PTL3X concentration of this one and then concentration of this one also. Whereas in this case when the solvent is there, you can also add the term solvent here in this case. So, this is how the influence of solvent can also be added to the rate equation. Since S is in vast excess, that means solvent, S is solvent, is in large excess, its concentration is unaffected during the reaction. Literally there is no change, and hence it can be considered pseudo first order condition. By comparing equation 1 and 2, what we can get is this is the one. Simply by comparing we get K1 equals K3 into the concentration of solvent. If the solvent is a potential ligand such as water, it competes with Y, the entering group, in the rate determining step of the reaction, so that X can be replaced by Y or S to begin with. Yes, X is the leaving group. Substitution of S by Y takes place in a fast step, that is non-rate determining step. So, therefore, two pathways by which the reaction probably proceed are represented in this one. For example, this is a typical reaction here. So, that we can see first initially before X is leaving, S comes here and then it establishes this intermediate, and then this intermediate would react with Y to give the product in the fast step. That means the decrease in the rate constants with sterically bulky ligands Y or L is an indicative of associative pathway favoring both the terms K1 and K2. So, that means the steric factors when we are considering, we have to consider the ligands already present on the metal such as L and also the steric bulk of the entering ligand Y. Both has to be considered to understand about the nature of the pathways. But here very clearly one can tell about the decrease in the rate constant with sterically bulky ligands indicates the associative pathway. That means when associative pathway is there, that favors both the terms K1 and K2. In majority of substitution reactions of square planar platinum 2 complexes, yes, stereochemistry is retained. You should remember, in majority of substitution reactions of square planar complexes, stereochemistry is retained. The entering group occupies the leaving group position. The entering group occupies the leaving group position. An associative or IA mechanism involves a 5-coordinate intermediate or transition state, and since the energy difference between the 5-coordinate geometry is small, one would expect rearrangement of 5-coordinated species to be facile unless, for example, it is sterically hindered, that means A or IA, or its lifetime is too short like IA. You have to consider. So, once again I tell you, in a substitution reaction on square planar complexes, the stereochemistry is retained. The entering group occupies the position left by the leaving group. An associative mechanism or interchange associative mechanism involves a 5-coordinate intermediate or transition state, IA transition state in A intermediate. Since the energy difference between different 5-coordinate geometries is small, especially in IA, one would expect rearrangement of the 5-coordinate species to be very facile. For example, this is the one I am telling you, very facile, unless, for example, it is sterically hindered, A or IA does not matter, or its lifetime is too short, in that case it is IA. The stereochemical retention can be envisaged as shown in this figure here. You can see in this figure. Why does intermediate or the transition state species has a trigonal bipyramidal geometry? So, that means now the question is, if associative mechanism is followed exclusively, with square planar complexes during their substitution reaction, and it increases the coordination number by 1 in the intermediate, that means going from 4 to 5. In that case the preferred geometry is trigonal bipyramidal. You can see here it is added, now it is revert back to square planar geometry after X leaves. That means here it indicates substitution is completed. Now the question is why it adopts trigonal bipyramidal geometry, why not square pyramidal geometry? Square pyramidal geometry, it can come and attack something like this, and then this can go and it can revert back to square planar geometry. So that is the thing. Now this is the time, appropriate time to bring the concept called trans effect. Trans effect is very important when we talk about the substitution reactions of square planar complexes. Perhaps you are wondering why I did not bring the term trans effect, or why I did not introduce trans effect prior to the discussion on square planar complexes. Of course, I was waiting for this juncture to introduce trans effect. The choice of leaving group in a square planar complex is determined by the nature of the ligand trans to it. This is the trans effect and is kinetic in origin. That means, in other words, I can also explain the ability of a ligand to labelize a group trans to itself, so that the entering ligand can occupy that position is called trans effect. That means the labelizing effect of a group trans to itself during a substitution reaction to make way for the entering ligand is called trans effect. Let us look into the preparation of well known complexes of cis and trans platinum. That means PtCl2 NH3 twice. It is a square planar complex, you all know, and it shows geometric isomerism cis and trans. So that means how cis and trans complexes can be prepared using trans effect. So how trans effect operates in substitution reactions of square planar complexes, we can look into it just with the beginning of the understanding of the formation of cis and trans diamino dichloroplatinum complexes. So look into it here. We started with here tetrachloroplatinate. Here you should remember, of course, we are adding ammonia, and by spectrochemical series also you know that the moment a strong field ligand such as ammonia comes, chloride, a relatively weaker ligand, it leaves, yes it goes, and now we have 3 chlorides are there and 1 ammonia is there in this one, and next continue adding another molecule of ammonia, so that replaces another one, and then we get a cis compound here. So that means we are getting a cis compound, means either replacing this one or this one, not this one. So we are getting the cis product here. In contrast, we started with tetramine platinum 2 complex. So now in order to make a chloroamine complex, we have to add Cl minus. When we are adding Cl minus, obviously one of the ammonia goes, does not matter which one goes, we end up getting a 3 ammonia and chloride comes. Next, when we add NH3, this NH3 adds to a position trans to the chloride here. So that means that results in the formation of trans compound here. So trans compound is obtained. That means tetrachloroplatinate, if you take and add in the sequential order ammonia, that leads to the formation of a cis product here. On the other hand, if you take tetramine platinum 2 complex, add chloride in 2 steps, that leads to the formation of trans compound. So this was the beginning of the reactions that led to the understanding and explanation of trans effect, and hence the substitution reactions in square planar complexes. And in case of octahedral complexes, this trans effect may or may not influence the substitution, but whereas in case of square planar complexes, this trans effect influences a lot, and it has tremendous influence on the rate of the reaction and also in understanding the mechanism of the reaction. So the general order of the trans effect, that means the ability of ligands to direct trans substitution, spans a factor about 10 to the power of 6 in the rates. That means their influence is remarkable. If you can see to what extent the influence is represented by this order, that indicates to what extent this trans effect has an influence on the substitution reactions in square planar complexes. The trans series is given here. For example, if you just look into this one, you should be able to see how a ligand can be replaced with another ligand can be clearly seen. So, this is the trans series and one can also extend it adding some more, but these are the important ligands we come across when we perform substitution reactions in square planar complexes. So, now with this information, now let us look into the classification of ligands. In my previous lectures when I was talking about classification of ligands by donor atoms, so I tried to convince you about the type of ligands we have and also how they can be classified. That means classification of ligands one can do into 3 categories and their characteristic properties have been thoroughly explained in my previous lecture. So, in order to understand the trans influence of these ligands, one has to look into different trans theories. That means the 3 class of ligands I classified and told you are the pure sigma donor ligands and sigma donor and pi donor ligands and sigma donor and pi acceptor ligands. That means we do not have a very general trans theory to explain the influence of these ligands on substitution reactions, but we have to go for different theories depending upon the nature of the ligands we are using. That means since we have 3 categories of ligands, we also should have 3 categories of trans theories. That means we cannot have a general theory that can explain the influence of all class of ligands. Okay. So, we have to have conveniently 3 theories to understand the trans effect of these 3 class of ligands. What I will do is in my next lecture I shall elaborate on trans effects and what are the trans theories we have at our disposal and what kind of ligands would follow which theory, all those things I shall tell you in more detail. So, until then have excellent time in reading chemistry. Thank you for your kind attention.